Hello, I'm Dana Sheehan. I'm one of the content developers for AIND, and I'm going to help you out today by walking through the Recognizer project. This is the project for recognizing American Sign Language gestures, and it's project 4 for the first term, and we'll be working our way through that. Okay, so the first thing that I'm going to do is, I guess, share my screen. And the way this is going to go is I'm going to walk you through the project. We're going to talk about the environment that needs to be set up. We're going to talk about the tools you need. We're going to step through the notebook, and then that'll probably take 45 minutes of the time, I'm estimating. At the end, I'll answer questions if there are any, and we'll just go from there. Okay, I'm going to share my screen. Okay. Now, the first thing you do is you're in your classroom, and this is clear down at the end. We've done planning, you've done the first 3 projects. Hidden Markov models is the section that you want to take a good look at. You should go through all of these lessons in HMMs, because that is the core of the Recognizer project, is using HMMs and implementing them to figure out the gestures of sign language speech. And that is talked about quite a bit in these lectures, so you'll want to go through these. At the end, you'll get to the sign language submission page, and this will give you an idea of what you need to do for the project. There's 3 main parts of it here. There's setting up the data, selecting the models, and then building your final recognizer and running some test samples against it. To start out, you need to have a good environment set up. So I'm going to go back to the Anaconda environment and just go over that really quickly. I know you've gone over already setting up the environment, but there's a few things that are used in the 4th project that are not used in the other projects. So if you didn't set them up before to include all of that, you need to have the full environment for this. One of the aspects of it is the HMM Learn library, and as well as pandas. But HMM Learn has to be added in addition to the environment, and what we need is we want the development version, which is 0.2.1. The standard version, if you just do a pip install HMM Learn, is going to be 0.2.0, and it doesn't have some errors fixed that were fixed in the development version. So we want to build the development version, and there are instructions here to do that. The development version fixes some problems with calculating the log likelihood, which you will run into if you don't upgrade, I believe. Okay, now there's one other problem. You're going to be using a Jupyter notebook, and if you have done these before, you may be already familiar with using that with Conda. But something happened recently. The Conda developers created a new version of Conda for Python 3.6, and unfortunately, Python 3.6 is not compatible with the extensions that are included with previous versions of Conda, and so they are no longer building those in with Jupyter. So there's a way around this, and this is a little complicated, but recently this little section on tips for Jupyter notebooks has been added to your Anaconda section. So if you've had trouble with this, you might want to go back and look. Basically, what you're going to do is you're going to create an environment that is just to handle Jupyter and the notebooks with this extension in Conda. And then what you're going to do is you're going to activate your directory with this notebook environment, and then once you're there, you'll be able to use the notebook as you should be able to, and I'll show you that in a minute. But I just wanted to kind of point that out, and then when I go through it, that's the way I'm going to do it for you, so you can see how that's done. If you installed your Conda a long time ago and it's 3.5 and that's all built in, you may have no trouble at all, but newer installations may have a problem here. Okay, The next thing to do is you're going to want to clone the repo. The repo is at AIND Recognizer, so you'll want to clone that to your computer just as you have other projects. And taking a look at it here, we have a data directory that you don't have to do too much with, but if you want to look at it, feel free. We have the README, which tells you that you are going to be using these various libraries, including HMMLearn, and points out that you need 0.2.1 again. You are going to be using a notebook. It tells you how you can run the notebook. And it tells you just a little bit about what the data is all about. What we're doing here is we're using a data set of videos of gestures made for American Sign Language. And this wonderful database has already been set up for us. Well, not for us, but it was done as somebody's research project, and we're using it. So in this database, there are 3 different speakers, and as they make their signs, the information that's recorded is the location of their noses. So let me try to make this a little bigger so you can see it. So we'll have an X and Y of the nose location. We'll have an X and Y of the right hand location, and an X and Y of the left hand location. And these are the pieces that we're going to use. So what we're going to do is we're going to analyze data and create models for similar words done by the different speakers. The same word, if they all are doing go, or they're all doing the word John, or they're all doing the word chocolate, we will take all those copies and build a model for what chocolate or go or John should look like. Then we're going to test it with a test set that was also created in this data set. Now, we've pre-processed some of this data for you. This original test set is videos of continuous sentences. What we've done is broken those into words. So we're going to actually be using more of a dictionary and breaking those up into words and training the words and testing them. Just a little background there. Okay, so to get started, we're going to, like I said, we've got this repo we're going to clone. But in addition to the notebook that we're going to be working in, there's some behind the scenes data as well. You're going to be modifying my model selectors and my recognizer. So this notebook is kind of a hybrid. So these will actually be files that you'll need to modify with your IDE. So we'll go over that a little bit too to get you started. Okay, so let's go ahead and get the notebook going and see how that looks. So I have my terminal window, and I happen to be in Windows. So to activate this Notebook 3.5 that I told you about in Windows, all I have to do is activate NB35. This is just sort of a workaround for getting into Jupyter. And then now you can see that at the left side, I'm now in this Conda environment named NB35. And now I'm going to do my Jupyter notebook. I should also point out that I'm already in the repo AIND recognizer that I've cloned. All right. Now what this does is it starts a server for Jupyter. And it pops me right into it. Here I am. And you'll see right here the notebook. So you're going to click the notebook, and it will open that notebook up. Now, if this has worked correctly, you will be able to see the different kernels that are available. If you wanted to change the kernel, for example, you could change into one of these Conda environment kernels. Okay, AIND is the one that is all set up, and actually I've already got it pointing there. So that's all good to go. So now everything should be able to run. Okay, as you open up the notebook, you'll see that there is kind of a table of contents. There's 3 major parts plus an optional part if you're feeling ambitious. The first part is going to be working with the data and setting up a feature set. Second part is going to be training the model and choosing which models, doing some model selection, And the third part is going to be building the recognizer once you have the models that you want to test your dictionary, test as a dictionary with your test set. Okay, so taking a look at this, I'm going to go ahead and click on that and just give you let you watch this video. If you see here when we mentioned before, this is a video of one of the sections where she's going to say John fish won't eat but can eat chicken. And you'll see that sort of build across. And what we've got here is they're focusing on the right hand, and they're going to show you in here what's happening with the locations of that hand. And that's what the data is actually made up of. It's made up of the X and Y coordinates for the right hand, the nose, and the left hand. So let's just watch it really quick. You see that the X and Y are moving along with her hand, and that's the data that is going to define the different words. What we've done in pre-processing is break these little sections up so that they're actually just words instead of sentences. Okay, that should give you an idea about the data. And another thing that's being sort of thrown at you here, but is a wonderful tool to know how to use, is Pandas. Pandas is a wonderful tool for working with databases of information. And you also have a helper function, a helper class called ASLDB, standing for American Sign Language Database, that you don't have to know how this works too much. It's sort of there. You will use it some later, and so you can go look at it if you need to, but it's in a Python file in this sort of hybrid situation. To get started, you don't have to look at it, but just know that it's there to build a database and help you out. Now, what I've done here is I've simply executed this one cell. To execute a cell, is Shift-Enter will do that. And any Python cell, you can do Shift-Enter and it'll execute the Python. It does it in order. So if you try to execute something later on without having used this one, and it uses NumPy or Pandas, then it won't know what you're talking about and you'll get an error. So it really is sequential. Although if you change something in a Python file behind the scenes, you should be okay because we're going to set it up so that it will automatically reload those. But anyway, let's take a look at the data. This is video number 98, and it's the frames 0 through 4. And in these frames, the left hand and the X and Y, the right hand X and Y, and the nose X and Y are actually not moving at all. It's this right here. She's just sitting there because it's the beginning. If I had looked at more data, let's say, which you can play around with this a little bit, I could have seen, I should have done a Shift-Enter. I could have seen more data, and I would see some movement beginning to happen as the video starts for the word. Okay, so I'm going to change that back and look where it was. All right, now we're going to look at the data in an individual frame. This is actually data frame 98.1, so it's this frame right here. And this is just to give you an idea of how you can look at that particular frame and see all the data and how you can access it when you need to. And here's a picture of it. If you were to look in the database, there's some links up there and also on the README. You could find all the stills, you could find the videos for all of the gestures, and I encourage you to watch them so that you understand what's really happening here. I can assure you I watched every single one of them as I divided them from sentences into words, and it was very informative. I would highly recommend understanding the data you're working with, because that will give you insight later to what features you need to use and why you're having problems in different places if you do have a problem. Okay, the first thing is decide what features we're going to use. The raw features that are given are, if this was the origin, the X goes this way and the Y goes this way. So a location of 149, 181 is 181 down. That's probably the left hand. That's what the location is. Whereas the nose is 161 and 62. So 161 and not down as far. That's where the nose is. So anyway, that's what the X and Y are doing. Okay, if we want to define some features, we're going to use a ground truth. The reason the nose is even given in this whole data set is so that everything can be relative to the nose. The nose is considered the ground truth, because if you did some videos where the person was sitting slightly to the left or slightly to the right, then that's sort of, think of that as the center of the body. And since everything is a gesture with right hands and left hands, then it's all related to the center of the body. And that there again, that's what's important about what the data is trying to tell you. So what we've having you do here is to take the ground right, left hands, X and Y. And what we're doing here is the right hand ground Y is going to be the difference between the right hand and the nose. Okay, so we can execute this and we can see that this is an easy way to add another column right here to the pandas database that you're building. So your database is named ASL, and you've just added another column called ground RY. Now the next step is you're supposed to try it yourself. Now this is just a little practice thing to kind of get you going. And spoiler alert, I'm going to go ahead and give you this, but if you don't want to look away. But it follows the same pattern here that you've just been introduced to. I'm going to go ahead and put it in there and execute it. And the reason I'm doing this is because if I don't, we're not going to be able to do much else in this notebook that I can show you. Okay, once you do that, you will see that not only is ground RY showing up, but now ground RX, LY, and LX is showing up. So this is how we can create some features. And you're going to be able to do this with other features that we'll be asking you to do later. So once you've done that, you could get features for a particular video and frame in this new feature set. We're calling it features ground here. And you can do that with any kind of features you want to create. Okay, once we have some features, we're going to use some helpers that are already part of your starter code to set up a training set. Now there's a training set and there's a test set. And this is, these were already set up in the original data set that this is taken from. So we've kept that split, and it's split so that the test set is representative of the training set. In other words, the words that are used are evenly distributed in the test set relatively to go with the training set. So the idea is we want to train on the training set and then test on the test set. Okay, and see how we did. So here we're going to go ahead and now what I just did there was I printed all the words that we just trained, or that we just pulled. We didn't train them yet, we built them. Built a training set, and the training set is taken from the data set and will have these features, these feature ground for each word. There will be all the feature ground sets. Okay, so now we have some training data based on these features for all of these words. For example, if we wanted to look at the word chocolate, which is part of that, this is what it looks like. We now have ground RX, ground RY, ground LX, and ground LY, a whole series of them. And the way this is set up is because of the way HMM Learn needs it, we have 3 examples. This tells us there's 3 examples. And the first example has 17 time steps. Second example has 20 time steps. And the third example has 12 time steps. It's set up this way because that's the way HMM Learn needs to have it set up in order to create a hidden Markov model. So that's why it's set up that way. We could have looked at a different word, and you could try this. Maybe I want to look at the word Anna and see how that looks. And if you look down here, there's only 2 instances of Jana in the whole set. So that's not very many. That's pretty sparse. Let's look at John. John is the most common word in this data set. It's so long that it's been truncated by the software. And this list is however long this list is of the lengths of each of the sets. That's how many Johns there are in the data set. So we could try this with any of the words here just to take a look at it, but I'll just put it back at chocolate. But you can play with the data to your heart's content here. And here's a little trick. You can click this to make it shorter or even make it hidden. So that's kind of handy. Okay, now right here, this is a demonstration of other things you can do to get some statistics. It happens that this database has 2 different women speakers and 1 male speaker, as those pictures we showed earlier. This data set is made up of those 3 speakers. And as you can imagine, they don't look quite the same when they each have their own style. When they make the sign for, let's say, chocolate. One might have longer arms or just naturally make the symbols more compactly to their bodies. Some are taller, some are shorter. So you might want to think about finding what the average distance that they move their hands out to, like for the X or the Y, or you might want to do something else. This is a way to do it, to find the means, which you might find, well, you will find useful in doing the implementations. Okay, so, and if you take a look at it once you do this, where you can build, you can add this as another feature, which you can then use to manipulate things however you want them. Okay, so you could, just as we added these features, we can also add a feature that moves across these groups. And this is your pattern for a way to do it. I'm not saying it's the only way. Now you have to try it on your own, and I'm not going to show you how to do that, but it's a very similar process. You can do it for all kinds of things. In this case, I think we have it set up to do it with standard deviation. So you would have mean and standard deviation for all of the different speakers so that you could normalize if you needed to. Then we get down to the actual implementation, this submission section. And what you'll do here is you will write the code that you need to write to create a normalization, polar coordinates. That would be a polar coordinate for, in this case, would be, if you think about the data again and how it's being created, imagine that the origin is the nose, and a polar coordinate would be the radius as far as this distance from the nose to the hand, wherever the hand may be, and the angle would be the angle from some line. Now, normally, if we play with the unit circle, you might remember that that angles go around like this. They go where the X is here and the Y is here. But we've asked you to do a little trick where you swap the X and the Y so that the angles will actually be going around. I think they go this way. Oops. They will go this way where 12 o'clock is the 0. And the reason is that wherever the 0 is, 0 goes one way, and just on the other side is 2 pi radians. So you have a jump from 0 to 2 pi radians. And if you take the angle difference from here to here, you'll have this big jump. But if you think about the data again and what the speaker is really doing, the speaker is not going to be putting their hands across the top of their head, but they might very well be putting their hands across here. So that may have been very confusing when I just said it, but that is right here where it talks about use the np-arctan2 function and swap the x and y axes. That's why. It's because of this discontinuity. So once you've done this, you'll answer a question and you'll run the unit test. Your unit test should pass. You notice that these don't. One of them does. We have an E is a failure, a dot is a pass, EE. If they all pass, it'll say so. This says 3 failed because they haven't been implemented. The only one that's implemented right now is the ground features. Okay, that's part 1. So now at this point you have your data sets all set up. You have a training set that you can build by simply running the training set. And now we get to more complicated parts. The model selection. Okay, we go through a sort of a little tutorial here where you can train, shows you how to train a word using, first you build a training with your features, and in this case I think we're going to be just using the ground features as an example. Then you're going to get the x and the lengths. Those are the 2 big parts from above where, when we looked right here, if I was getting the x and the lengths of the chocolate, for example, this is x, all of this data, and it's all concatenated together, and the lengths are the 3 of the lengths of the 3 different examples. So the first 17 of these are the first example. The next 20 are the second example, and the final 12 are the third example of the word chocolate. That's what x and lengths mean. Okay, I have to find where I was. All right. So in this case, we're going to go ahead and train it on a demonstration word named book. It's telling you that trained it for 3 states. It's because we used a default, let's see here. We use this number here. So here it's explaining how to do the training. All right, so we told it how many states we wanted to train it on, and then we got some log likelihood. Okay. Now, if we were going to look at the statistics, we've got a little routine here to look at the statistics for those 3 states. You'd have to kind of remember from the lecture what HMMs are doing. You'll have a mean and a variance for each one of the features. So we have 4 features. So we're going to have 4 means in the 0 state and 4 variances in the 0 state. And then similar for each of the hidden states. Now, in this case, we're going to just try it. We're going to train the word chocolate, and we're going to look at those states. So for the word chocolate, for example, we've got these mean and variances in 3 states, and we're going to take a look at them. Now, if I were to look, we'll look at that in a minute. If I were to look at this, I could see that, let's see, for the first feature, all of these are the first feature. So I have the first feature in 3 different states. The first time the mean is negative, the variance is 16. The second time the mean is closer to 0, and the variance is a lot bigger. If the variance is bigger, that means it's wider and flatter. So let's take a look at it. Sure enough, this one is at a negative number. This one is closer to 0. The green one is closer to 0, and it's a little shorter. Its height goes to a little over 0.05, whereas this one goes clear to 0.1. So it's the one with less variance is a little narrower. And you can try this with a number of different words just to get an idea. The kind of the hairiest part probably of the project is the model selectors. And for that, you're going to have to read about using these different ways of selecting a model. I just want to briefly go over that. If you or have a big training set and then you have a test set, the test set should be preserved when trying to decide which model you're going to do. What we're going to do with choosing models is deciding among whether we want 3 states, 4 states, 5 states, 6 states, 7 states, which one is the best. I mean, in the lectures, Dr. Starner just kind of arbitrarily said, well, the word I or the word we looks like about 3 states. But we're not going to do that. There may be one set of states that's a better model than the other. And how do we know what that is? One way is to look at the log likelihood of the different states and see which one has the best number. But if you just do that across the training set, it's kind of the mouse watching the cheese. If you just keep increasing the number of states, then probably you're going to get a better and a better likelihood, but you're overfitting. So we want to use cross-validation and only train on part of each set and then test with a smaller bunch. But we don't want to use our final test set because this is a hyperparameter essentially. This is really the only hyperparameter we're going to be looking at for this project. So cross-validation is a way to do that, and you can read up on how to do that. Another way to do that is to penalize the more complex models with a method called BIC, Bayes Inference Criterion. And then a third way to do that is instead of penalizing complexity, you penalize the similarity that there is between other words. Since we have a fixed dictionary of, say, 100 words or however many it is, what we'll do is instead of picking the model with the best likelihood, we pick the one that's the best likelihood, but not like the others, the most likely to be distinctive. So that's what those 3 types of models are. And you're going to have to implement those, and you're going to have to go into your own IDE, which is provided. We have a starter code for you in My Model Selectors. If you look at it, the main class for Model Selector has a base model. The base model is used by Constant for selection. It basically just calls the base model and will do some plain number. If you use that, then you could conceivably train all of these by just saying, I want them all to be 3 states. But what we want you to do in model selection is to use the cross-validation model, the BIC calculation, and the DIC calculation to use those for your selection. And then to compare those later once you get your recognizer built. So for cross-validation, there's a little bit of a tutorial here on how to use k-folds to, let's say, try create different folds for vegetable. For example, what it does is it gives you an index of which versions of vegetable to use. And if you only have 2 instances, you're going to have to just make some kind of assumption. But in this case, it looks like there's 6 different examples of the word vegetable. So it's divided it up into some random way. And then what you do is you'll create your models with these 4 and then test it against these 2. And create your models with these 4, test it, create your models, test it. And then decide from there which you want to use. BIC uses the equation that's given to you, and you can look at your references here. DIC is a similar idea, and the reference for DIC is given to you. It's this paper by Alan Bain, and it also has a lot of good information about how BIC works. And good look at that to really understand how BIC and DIC work. Both of them. It's really a little different. The idea is the same. You're penalizing it by different. I mean, I think in this one you're looking for the highest positive rather than the highest negative. So get back to the. Okay, so you're going to have to implement each one of those model selectors. Again, answer a question about the advantages and disadvantages that you're seeing or expecting. I think you are you end up running these with, let's see, you run these with, I think it gives you 5 to run it with, but you're going to fail on these selectors because these are not implemented yet. So of course it's going to fail. All right. So then you will get those done. You'll run the unit tests. You want to make sure these pass. Of course, they will not pass. They should fail. You need to answer these questions here. And then what we'll do next is actually the recognizer part. Okay. So the recognizer is basically you've got a dictionary, and you're going to train using some feature set that you've chosen of the ones you created, and training using model selection that you've tried. So if you've got 4 different feature sets and you've got 3 different model selections, then that's 12 right there that you could try. You don't have to try all of them, but you know, it's kind of interesting too. In order to try them, you can just kind of duplicate some things. Oh, this is going to fail because of course there's no recognizer. But what you can do is once you get down here to the implementing these, you can, here's kind of a basic one right here is just based on constant selector. So it just kind of a baseline for you. Using ground and constant selector, you can, once your recognizer is built, you can train all the words with the constant model selector, which isn't really doing anything except saying, you know, always 3 or whatever it is. And with just the ground features, which are kind of plain vanilla, and you can run that and get some result. What it will do is it will show you the test sentences that you found, and it will show you what your errors were, and it'll give you an error rate. So that's all taken care of with these show errors helpers. So if you follow the to-dos, you get that. Then you can create as many of these as you want to try out with alternate model selectors of the 3, alternate feature sets of the 4 that you've got, and see how it turns out. Then you run your recognizer unit tests, which is basically making sure that your recognizer works. And you should make sure that you you complete the answer, and you also should have a WER rate of better than 60%. You should be able to get close to 50%. But probably not much better than that. If you can get better than that, you're doing amazingly. But you should be able to get better than 60% if you do something other than some of these, something like constant. That's probably not going to get you there. Okay, so that's basically it. Then once you have everything passing, you can create your HTML and follow the instructions and turn in the My Model and the My Recognizer per the instructions. This optional part is very challenging. For that, you would need to read more about engrams, and I'm not really going to talk about that in this walkthrough, but it's challenging, but you learn a lot if you even attempt it. So good luck with that. Meanwhile, I think it's probably time to answer some questions. So I'm going to go and see if I can figure out what questions have been asked. Oh boy. All right, I'm going to try to go up to the beginning here. Okay. I see we have a pre-submitted question from Octavia. Okay. Why is CV presented as a model selection method when in fact the selection criterion with the selector CV is log likelihood, and CV could be used with BIC and DIC? That's a very good question. You're right, the selection is log likelihood, but what we're doing is we're treating the number of states as an actual hyperparameter. Therefore, we need to use select using you're correct that it is log likelihood, but we need to use CV to divide those up. Now our data is rather sparse, so what happens, the reason we want to try it with BIC is because we don't have a lot of different instances of some of these words. And yes, you could, I guess, use CV with BIC, but you don't have to, because BIC is already taking care of working past the overfitting problem. The reason for using CV and using log likelihood, but doing it with cross-validation, is so that we don't overfit. And BIC takes care of the overfitting problem by adding a penalty for complexity. DIC does something similar, only instead of adding a penalty for complexity, it's really taking the universe of words that you have, our dictionary, and looking for which log likelihood best discriminates one model from the rest. And I hope that answered your question. It would be better if we had a lot more data and use the cross-validation in some more robust way. We are kind of skirting on using the test set. If you were to go back and forth with your different features and try different ones to see how they turned out on the test set, we are kind of violating one of the tenets of machine learning. So I would encourage you to just kind of go with the feature sets we've chosen and pick one that makes sense to you as a fourth one, just for trying and analyzing the results when you're done. But once you see the results, as long as it's working, you should not be going back and forth and tweaking your model selection. Okay, so I hope that answered it. Okay. Next question, also from Octavia. Speech is continuous. Our test set has already been pre-segmented into tokens, but in real life, shouldn't tokenization be part of the recognizer? Yes, it should. This was an easier problem to explain and use in the classroom, but continuous speech has the problem with, sometimes the problem with one word runs into the other, whether it's spoken speech or gestures. And yes, it's a different problem to solve. So that's been done, and that was actually done with this original data set, was an automatic gesture recognition. Okay, so let's see, I think this is also from Octavia. The recognizer would receive a continuous input and the output in sequence of discrete items, each assigned a class, i.e. a word. How would we go about doing that? Well, I'm afraid that's a little outside my scope for doing this, since I haven't done it, but it is in the papers that are associated with this data set, and I would encourage you to delve into it that way to find out more about it. We are going to be doing some of that in speech recognition in the voice user interface class, though. That's in term 2. That will be continuous speaking. So if you're interested in trying it there, I'm welcome to come and join that class when you're done with this one. Now, do we have any other questions? I'm not seeing any. Am I missing any questions, Elizabeth? Oh, I think there's some questions coming. Mauro Restuccia. How can I be sure this is properly implemented? Just passing the unit test is enough? No, the unit tests are very rudimentary. So I guess the way to tell if you're doing it correctly is to see what kind of results you get. You know, if you're not getting results that even make sense, then you'll be pretty sure that there's an error there. I think that you'll probably need to maybe reach out online if you have a particular issue that makes you think it's not implemented correctly. I think that you won't get decent results if you haven't implemented it correctly. Now, we do have plans going forward to add more tests that will be a little more informative for you, so that to help you along with that. Another thing you can do is maybe create some print statements in your code so that you can see the inside of it and satisfy yourself that it's done right. Octavia, thank you. Okay, and Gonzalo, regarding part 4, what would be an acceptable result using 3-gram model? If you look at the paper, let's see if I can find the paper. Let's see. There is a paper. If I can't find it, I may have to post it, where the group that actually created this data set did, create those n-gram models, and they had significant improvement. They were doing automatic speech recognition, so they were doing the continuous signal. So it's hard to say, but you should have significant improvement if you were to implement a 3-gram model. I think they had better than 80% accuracy. So it's hard to say if you could get quite there with the word models, but it should be significantly improved. There is some difficulty with actually implementing this. I think you probably need to tune some kind of ratioing of how much of the model is due to the likelihood that you calculated with your selector, and versus the likelihood that they present for the n-grams. So that's all I got on that one. I don't see any more questions. I think we're about done. I think that's probably all. Okay, I don't see any more questions, so I think we'll call it a day, and thank you all for tuning in, and good luck with the project.